from planes, but also from UAVs. And this is especially my personal focus. I'm into image-based methods from photogrammetry, remote sensing, and of course, computer vision. And the typical product we usually derive from these sensors, either from space or from the air or from the ground, are, in my case, digital 3D elevation models. And what I like what I like to do with these measurements, and why this is my favorite topic of measuring things, is that we have this contactless measurement. It is non-invasive. We do not harm the environment anymore, and we can do multi-temporal monitoring. And when you imagine that you can, for example, use satellites to observe the Earth in 3D, and satellites are just turning around the Earth and so on, then you get a lot of 3D models from different timestamps. And when you insights into the changing spatial environment, and we call this 4D monitoring. So this 4D topic, or this 4D term, better said, is maybe not so clear to anybody, because 4 dimensions, what does it mean? We have there some different perspectives on this 4D term. So on the one hand, we have this technical analytical perspective. So this is what I said, modeling and visualizing spatial temporal phenomena over the time. So we have 4 components. Yeah, we like to investigate and we like to communicate. But you can also understand 4D from a more metaphorical perspective. So you can understand it as some steps you have to fulfill from capturing until presentation. So first, capture the data. For example, you do your first measurement, having your first UAV overflight, or you have a follow-up measurement. You have a different campaign, and you like to use these 2 measurements to get more insights what happens over the time. For this, you need to manage the data. You have to see that they are the same coordinate system. They have to be in a specific coordinate format, for example. And then you can use the data to analyze. And you can use them to find patterns, to explore specific trends. And when you have this knowledge, then you have the last step, the presentation, which is the experience part here. Then you have the thing you have to communicate to the public to convince them that something is happening on the Earth. So, and this is also some kind of 4D understanding. In Germany, we call this principle EWAP, but here in the English translation, we can call it CMAP. Maybe this is something really nice to recognize. Capturing, managing, analyzing, and presentation. And as I already said, I'm working in this discipline for several years right now, and I just have a quick recap that I would like to show you. Just some projects I worked on in the past, that you have a feeling what she's talking about, what she's doing with all the data. So the first project when I started my career in this scientific environmental monitoring thing was in 2013 in the Institute of Cartography at the University of Dresden. And here I used satellite images. So everything in my case started with the satellites, freely available optical satellite imagery, this time from Landsat and from Astra. There was no Sentinel this time available. And I used the pictures to track specific points in the images on a glacier tongue. And by comparing different timestamps, here we have already the timestamp character, I just can follow the points, so I can get trajectories of some, because when you see here in the picture, you have these large rocks and some crevasses, and you can track them in the images, and then you can estimate some kind of flow velocity. Yeah, this was the first project, was my master's thesis, where I worked in this discipline, and the result was a map, a flow velocity map of a glacier region in the Tian Shan Mountains. Then I applied the same method that was developed in my master's thesis to another region, not that far from you guys, in Patagonia. So here we are in Torres del Paine, which is pretty famous national park for tourists. And we have this Great Glacier. The Great Glacier is pretty interesting because here it looks like more or less a hand with 3 fingers. and you have some kind of nunataks. We call them nunataks here in between. And there's a lot of stuff going on in this glacier. And a colleague of mine, she's now also working at the University of Applied Science in Dresden. She installed a camera system at these nunataks, observing the glacier tongue from the front. So she gets insights into the velocity from the close range perspective, and I validated her measurements from the remote sensing perspective using the optical satellite imagery. So in her case, she got a really, really dense and temporal high reserved field of velocity vectors, but this was not possible for me because I only had some timestamps of 1 or 2 years, but I got a more, how should I say, spatial, and a much higher spatial resolution, so I could cover the entire glacier tongue, not only the front. But it was pretty successful, so we got more or less the same results in the front area with the data she observed or she acquired and I acquired, and so we can validate our measurements to each other. We had a second project, so all these projects were in cooperation with the Universidad de Magallanes in Punta Arenas in Chile. And here we have some kind of early warning system I was already talking about. So this was some years before the drones, or we usually call them UAV because drone is a more military concerned term, so I prefer UAV. And but UAVs were just they come into our interest for surveying, and we thought with the guys there about a monitoring system for Rio de las Minas, because Rio de las Minas is has a catchment area inside the forest, and it happened not rarely that you have some kind of landslides in this area which block the river. Then you have heavy rainfalls and all the mud just runs without any knowledge beforehand to the city. And when you have the option to just have an autonomous drone flying along the river, capturing some pictures, we can use the pictures to calculate 3D models. We can do 4D change detection when we do this on specific dates. Then we can look, is there any landslide happening? Is there some block in the river area? And you can see the results here. So we did this by helicopter. As I said, it was before this drone area started, but this is the same approach I was talking about. You can do this from helicopter, from UAV, from satellite. I will show you an example how you can do this from satellites, and you get spatio-temporal information on the landscape. I think this could be also an interesting topic for you and your area. This was some kind of, maybe it's not that much in the discipline of this 4D measurement. It's more in the 2D, 3D topic. This was my PhD project where, just simply said, I programmed a smartphone app which you can use to estimate the water level. So by intersecting pictures you captured by the smartphone with 3D data that was, for example, captured by Google. Coming back to this 4D topic, which is the topic of today. So it's the same method, but a different topic here. Here we are interested in how glaciers are changing, also 4-dimensionally, so with the high spatial temporal resolution. And the first tests, or the first data we captured, was at Bellinghausen Glacier, which is in King George Island, Antarctica. Really interesting study area, just saying. And here we also get these 3D models, and here just getting a first feeling for visualization. This is not a true overflight. This is an overflight over a 3D model with really high resolution, spatial resolution, and you can already get really nice insights without being there, because it's pretty hard to get there. So, and when you have this multi-temporal data, then you can do, as I said, the calculation of some changes, if there's something happened, in this case, if ice was melting. And this was the prototype for a big project of our German research funding organization, which is the DFG. And this project is an ongoing project. My colleague is still working in this topic. And here we did this investigation with a bit more detail, but in Norway. Because I will just focus on this example later, a bit deeper in my topic, but this is a pretty interesting glacier for method development. And I'm not a nature scientist, so I'm an engineer. I like to develop solutions for problems, specifically in the topic of environmental monitoring. But more on this topic in a few seconds. Yeah, just to leave the area perspective, a quick example from Finland and Lapland, where we do the same, but not from UAVs or drones, but from game cameras or wildlife cameras. Somebody say game, somebody say wildlife. And we just installed 4 of them at some kind of birches, and we're observing a riverbank, which is on the other side of a really interesting river, which is pretty sensitive to climate change. This river has a meandric form, and when there is something happening with the groundwater, then you have some kind of cutoffs of these arms and new arms just forming. And people from Helsinki University are really interested in how this river is shaped, which things have impact on the shape. And the riverbank, which can cause landslide, and then the blocking of the river itself is one of these really interesting things or regions of interest. And you also have here in the center a new kind of visualization. So this is not this area perspective. So you have here the close perspective, the close range perspective, and each point is an event we detected in our 4D models. So we investigated how the bank is changing. We installed the cameras in 2020 in October during Corona. It was crazy to get there and install the stuff. But the cameras capture pictures every 2 hours. They are triggered by some time interval there. And now we have almost 6 years of data captured, thousands of pictures, but we get a really high spatial temporal overview of what is happening, and we can correlate the data with other than sensors. For example, with rain sensors, and we can see and can draw some conclusions when, for example, landslides happen. Is there a specific rain event close by or something else? So really interesting study area here, and really important also for the people living there. So I just come slowly to an end. The thing I developed for these waterline detection and intersection for the water level estimation in my PhD thesis, the same method could be applied to investigate glacier movement, but not only in pictures, as I have done in my master thesis, so in 2D, you can do it also in 3D. You just can track here the stones and the glacier tongue. Now here you have webcam pictures. So there is a mountain station here, and the webcam is mounted to the mountain station. And it just watches here this kind of, this is a rock glacier, really interesting, which is a lot of mass and stones that are connected by permafrost, but to climate change, the ice is melting. And so this this mass of rocks is moving and accelerating pretty fast. Really dangerous area. People are living here downside, and so this is really interesting to monitor, to see what is happening there, how many mass is moving and how fast, and by this intersection with a 3D data set that was captured in this area by using a UAV, like said before, we can do this intersection, and we can get this really high resolved field of velocities. We are the first people who can deliver such results of this rock glacier. And as I said, Corona happened. It was a tough time for everybody of us, I imagine. And I started working on this 4D glacier project, where we went to Antarctica, but also to Norway. And I was sitting in my office, and my plan was to travel to the glaciers, because in Germany we don't have glaciers. and but it was not possible at the beginning. So I just thought, okay, what I could do else. Is there any source of pictures that could be interesting by the temporal resolution, but also by the spatial resolution, and which is less expensive, some kind of low-cost imagery that we can use also for this for the monitoring task. And I came up with PlanetScope data. The PlanetScope constellation is really interesting because this is a nano satellite constellation which is developed in Bern, but also in Santiago. No, not in Santiago, but in San Francisco. Sorry. And the satellites are only 30 centimeter times 15 times 10. So like, yeah, a shoebox. Yeah, they also called shoebox satellites. And there are several hundreds of these satellites traveling, moving around the Earth. And they have really, really tight orbits to each other. So one satellite almost crosses the other one, and we get some kind of overlapping images in really, really short time intervals. And I usually use for the UAV pictures, for the close range pictures. Why not apply them to the satellite pictures? And it worked out. This data is free for research and educational purposes. And I developed a pipeline where you can use this data, which is not intended to be used for stereo reconstruction, but you can use them for this. And I also did this 3D investigation 2 times. Here we have also a glacier area in Pakistan, Shispa Glacier, which is pretty famous for its surging events. And I did this change detection. You can estimate glacier profiles. You can see the mass movement along the profile. So it was a really nice side project developed during Corona times. So you can see my focus usually is on glaciers, but not only, because as you already recognize, several methods you can apply in different areas. But why I'm so into glaciers, why this is my topic. Yeah, the glaciers are disappearing, and this is why it matters. So we have almost 1/4 of the world's population which depends on glacier-fed water. Yeah, so it's a really important natural freshwater reservoir, drinking water, agriculture, for ecosystems, and global climate change is causing significant changes to the glaciers worldwide, which is a problem. And this rapid melting also, another problem, causing sea levels to rise. For each country with a direct connection to the ocean, this is a problem. So this is a risk to millions of people in this vulnerable ecosystem. So key observations that must be made are the retreat of the glacier fronts. So we call it the glacier front line or glacier terminus, the ice thinning, and the total ice loss, of course. And this was the reason, and this is the project I like to dig into a bit deeper and tell you something about how we did this. So how we came to the results we now have in our office. So this was the glacier monitoring project, where we have the objective to develop a method to reliable mapping debris-covered glacier fronts. This is a specific thing. This also is a problem in the high mountains in Asia, because usually somebody thinks glaciers look like this. So you have this really nice blue ice, everything is fine. You can clearly see from the space where's the glacier, where's the surrounding area. This is not the case for rock glaciers, but also not for debris-covered glaciers, where you have this kind of mud, stones on the ice. And we need a method to also investigate these kind of glaciers and check how the glacier front line is changing. And you cannot do this from space by, for example, using spectral investigations, which is the normal thing people do. And our idea is to expand the usual method from this 2D investigation from space to 4D, using planes, satellites, UAVs, close-range cameras, doesn't matter, to calculate 3D models, co-register these 3D models, and check where are differences, because when we estimate differences, we know there was ice. Yeah, so this is the objective here, using this static dynamic part, so a purely geometry-based approach to get the glacier outline. In Norway, we applied UAVs with cameras, and in surveying geodesy, they have proven themselves as really cost-effective tools to create georeferenced multi-temporal 3D models. We call them shortly DTM, from image measurements. I just show you two pictures here from 2022 and from 2023. Orthophotos plotted here, and by eye you can see something crazy is happening there. There's only 1 year in between, and the entire ice area from here is gone here. This is a big problem, but we can use this data, and now we come to this investigation thing, what is meant by 4D in this topic, the analysis, by calculating a so-called difference of DTM or DEM, and along the Z component, we get now insights into the pure ice field that changed. How can we do this? How can we do, or how could we use camera images captured by a UAV to calculate 3D data? Maybe some of you know this principle, maybe some not. I just do a quick recap of this. So we are inspired by nature. We are inspired by our own human spatial vision. Everybody of us has 2 eyes, and most of us can use them to focus a point which might be far away from us or close to us by one eye and also by the other eye. And both eyes see the same object from a slightly different position. So you have to imagine when you have this light ray here, because we can see all the objects, all the color. Usually you have the sunlight. Sunlight is emitted, is reflected by the objects on the earth. The eye or the light is passed through our eyeball. And when you imagine that you have a light ray from this tree here to the right eye, to the left eye, you can already see there's some kind of intersection angle appearing here. Our brain knows about the position of our eyes, about the view angle of our eyes, so how they are oriented to each other. So we have a triangle that is arising here. And by this triangle, our brain can estimate this angle here, which is called parallax angle. If the angle is pretty small, then the object is far away. When the angle is large, the object is quite close. Maybe you know from mathematics, the steeper the angle, the more difficult to determine. This is why usually we can much better estimate qualitatively the distance to a close object better than to a far object. So in front of me, I can say, okay, this is maybe 30 centimeters away, but when I look to the far, I have no idea if this is 100 meter or 120 meter when I see a car which is far away. So we can estimate qualitatively the distances. And as I said, learning by nature, we can apply this principle using camera pictures. So when we have one camera standing here, another camera standing there, we exactly know the distance between the cameras. We exactly know how they look to each other, so how they are oriented, what is the rotation. Then we get the same triangle. When we have overlapping images, where you have the same point you focus on in the left picture, but also in the right, then you can measure the image coordinates here. You know this configuration, and you can now really calculate this angle, not only qualitatively, but quantitatively. So we can now use this principle to estimate true 3D coordinates. We can use it to measure. And this principle is applied when you do structure for motion. Maybe you heard about this principle. This is usually the procedure that is done or that is used when you use software, which is quite common right now, called Agisoft Metashape. This is exactly the principle. You have a corpus of images. You have a specific flight planning done beforehand, and you can see it right now. So now I start our UAV. And I plan that it should capture pictures. And you see the pictures overlap each other a bit. And so we have this specific points from several perspectives, and we can use this data, having a carefully done flight planning, to do this 3D calculation, the estimation of the 3D points on our glacier tongue. The problem is we are lazy people. We don't like to click several stones, as I did in the example before, that I say, okay, for this point in the picture, this pixel, I like to get a 3D coordinate. We love when things happening automatically, so there are methods that do this automatically for us. And a really famous method is just working like that. It tries to identify distinctive image points that are highly likely to appear in neighboring images as well. We call them feature points. What could be a point that is likely to appear in other images? So let's see, let's focus on this stone. The algorithm does nothing more than blurring the picture, and it checks, okay, is the stone any more visible? Yeah, again, yeah, it's still identifiable. So this should be a significant point. And this is automatically done by a lot of initially set points. When this point is considered to be significant, we have to describe the point. Yeah, so we have to describe the point by what does your surrounding look like? We need this information to find the point in the other images, where the surrounding might look a bit different because of a slightly different perspective. Maybe, there is a cloud passing by, so the light situation is a bit different. But in general, there should be more or less constant contrast situation compared to the neighboring pixels. So we calculate something called gradient. So the definition between the contrasts of 2 points. And we do this for a 8x8 usually surrounding, and so we get 128 values that describe the contrast relation from our point to the neighbors by these gradients. And we do this for all our identified points, not only in one picture, but in all other pictures we captured, we have in this image carpet from our UAV. And then we can do some mathematically comparison of these vectors. We just check where is the difference at its minima, and then we got a lot of matching points. Yeah, and when we have these matching points, and this we just have to think on, okay, we have to precisely know where the cameras are standing, how they look. We may know this from our flight planning coarsely, but we call it relative orientation. So this is a mathematical step we have to insert to estimate these specific alignment. We only need 5 points in these 2 pictures, which are, we call them homologous. So we found them as matching points, and then we can calculate this constellation, and from this we get exactly these coplanary conditions. Coplanarity means that we have this triangle formally constructed. And then we can do the 3D reconstruction of all the other points we could match in the images. Finally, when we did this, we do some kind of optimization. I don't like to dig deeper into this. We can also apply here some input of other information. And finally, we got the result of the other picture here. So, which is a point cloud of all these connected points we detected. So we identified in the first step. We now know precisely the camera pose, which includes the position, but also the rotation or the orientation. And we also have a deeper understanding into the camera intrinsics. So when we usually look at the camera lens, there is written 80 millimeter, for example, for the focal length. But because you can focus a bit, there is some shifting inside the lens of the lens area, because you don't have only one lens, you have an area of lenses. And so 80 millimeter is only the first guess. Precisely, you more have, for example, 18.01 millimeters. And for this entire 3D reconstruction, we need to know these values very, very precisely to get right results. Because this is why this calibration also is happening in this structure from motion process. And of course, we are in geodesy, we get accuracy matrices to get more insights into how successful was our acquisition, our calculation, like standard deviation, reprojection error, and so on. This is nice. So for all these feature points we identified, we have now 3D information, but well, I think, or I hope that you conclude with me that this is not really visually appealing, and we don't get that much information out of this sparse point cloud. So we have to densify the point cloud. This is another step. When you know these camera poses precisely, then you can do some kind of pixel by pixel reconstruction. The principle is working a bit different. Don't let me go too much into detail here, but when you have this poses, then you can get the result on the right side here. And then you can also do further processing operations like mesh generation, texturing, editing, first analyze steps, of course, visualization. But we are not finished here, because this is the thing we usually do after one campaign. But as I said, we do usually a lot of campaigns. And in Norway, we started in 2022 with the first one. The last happened in 2025. Maybe there's a funding option for this year. Not sure about this, but I think it is clearly visible something, really strange is happening there. And we like to investigate this. So how much ice we lost? How does the crevasses changing? And what about the front line, which is our first focus we have in our mind? For this, we need a co-registration of the 3D models. Of course, our 3D models are more or less point clouds, because these are only point clouds at this stage. They have a georeferencing. But for these 4D investigation, they have to be precisely co-registered. Each time you have some kind of uncertainties and you have to correct them. For this, you need to know where are stable points between all the point clouds, and then you can use the points to calculate the transformation. The problem is, in these natural sites, you have no clue where all the stable points are. And this is the PhD project of my colleague at TU Dresden. He's still working at TU Dresden. And when you scan the QR code, you got a really nice paper of him where he just proposed his first steps, how to just geometrically solve this estimation, where are the stable areas and where is the changing part. To do this co-registration step. Let's assume we solve this and we have now our co-registered 3D point clouds. We can go into the third dimension, the 4D analysis. So now we can determine the glacier margin, also mass changes. We call this DOD analysis, and for mapping the glacier margin, we check the distances along the Z component. This was the map you already saw at the beginning. But really nice side effect, when you check the other components in your Cartesian coordinate system, you can also analyze, for example, how the glacial crevasses are changing. So this is pretty nice side effect and really interesting for our colleagues in Norway, which are glacier scientists. So they are working in glaciology, and they are really interested in how the crevasses are enlarging, how they're shrinking, what is happening in this topic. Well, okay. I think right now we have a lot of data generated. We have really nice, we got really nice insights, but I imagine we all agree that these kind of visualizations are more or less interpretable from experts. Yeah, they are not made for the public. So to convince the public that we have to do something in the world, we have to generate presentations and we have to make the processes visible. And there is a pyramid framework that was published by Eichner in 2023. The Eichner yeah, it's a couple, so this is why I'm saying the Eigners. They work a lot in the field of spatial time visualization, and they said that the data is conceptualized along 3 perspectives. So the key question is, what do we want to communicate? And there are, again, several dimensions, in this case 3. So we have to check where's the event happening we like to communicate. So in our case, it is spatial information, so the where is clear. Usually we work with this discrete spatial coordinates. When, what time frame you like to visualize, yeah? When the event is happening, and of course what. In our case, the measured discrete changes in a depth direction. And both Eigners just did a categorization of time-oriented visualization techniques, because you can't imagine, it's what, this is a lot. There's so many visualization techniques available you can use for this spatial time visualization. And yeah, they just try to classify them a bit better. And of course, we have here this time dimension, and we first have to decide what is the primitive we like to visualize. Do we have discrete time points, or do we have intervals? The arrangement, do we have linear events, or do we have something cyclic? So in Germany, we have the 4 seasons, yeah? So spring, summer, autumn, winter. Do we investigate something like happening in this cycling way? Could mean that we need a different kind of visualization. The number of variables. Do you only have one variable you like to visualize, or do you have several? The reference frame. In our case, we work with spatial data. Yeah, we work in geosciences and environmental sciences, but also geodesy. But there are also abstract data available. So there are specific visualization techniques for this. And of course, the kind of visual representation. So how you like to present your data. Do you have a poster presentation or a paper, bachelor thesis, master thesis? So usually your product you like to include your visualization is something printed, static, or is it something like an interactive display where the public can interact with? Yes, or do you have the option to show on the screen an animation? This is something dynamic. And of course, the dimensionality. Do you like to present 2D stuff or 3D or even more? Let's see what is possible. Making processes visible. I just like to take the pictures you already saw, the maps from the former projects, and do some kind of classification here using the principle of Eichner. So for static geodata visualization, the most appropriate option is the change map. This is something more for the experts because it's pretty hard to grasp. Usually we use this kind of choropleth map where you have a coloring of the areas by the variable you like to visualize. Here you have some kind of, you have to think on this, on the color scale or on the color scheme, because we like the map in a way that nobody has to consult the legend to check what is inside the map. Usually the colors should explain themselves. But here's something really interesting to keep in mind. So when we focus on this velocity map here in the center, usually, or at this time, when I was the cartography student, I thought, okay, I use green, a calm color, nature, relaxed color, when there's almost no movement, and red if something is on fire, there is a high velocity, and so on. But then I read the publication, and they have quite the opposite meaning, because they say when you just check the travel lights or the traffic lights, then red is the situation where you have to stop, green where you have to go. And when you nowadays check online maps which related to traffic information, usually you have the opposite color scheme. This is something many people just use the color scheme QGIS or ArcGIS proposed to you at the first time when you just click on please color my map. But I'd just like to convince you that maybe one or two more thoughts on this might be worth it. On the right side, you have this map from Finland, which we called quantity labeling. So in all these examples, we have intervals we like to visualize. This is a linear thing, univariate variable, we have a spatial context, static visualization. You can print this kind of visualizations in each paper, poster, and so on. But all these are two-dimensional. When I like to have more timestamps, I like to communicate, then one option is called small multiples, or also multiple windows. Here we have this Norway data set, and we have here this change detection. If you have even more timestamps, you can use a space-time cube. But you can already see here that specific changes might not be visible anymore. This is more a visualization that could be interesting if you have interactive options, so that people can rotate and move in this graphic. I think one thing that is getting clear here is that time always needs space. Visualizing time needs space. And this is the problem with static maps. Usually we lack of space, yeah, especially when we have these high temporal resolutions. To just make this visible, I need a really, really wide screen or paper sheet to just enlarge the cube here, that some or one can check the maps map by map. So what could be an option to solve this problem? If you have the possibility to use a screen, you may have the dynamic geodata visualization option, for example, using animations. Here you link the model time, you just use to capture your data, with the physical real time to present the geometry, but also the semantic changes using frames. So you have this time-dependent graphical representation. And here, this table just got some more columns. There are different ways how this could work. We can either have this frame by frame work, or this frame interpolation option. So frame by frame means that you have consecutive frames that show the time steps, or key interpolation means that you have some kind of morphing in between the time points. You also can have a difference in the perception. Do you have a true animation? We say that is an animation when you have 15 to 25 frames per second with a smooth motion. And this is pretty suitable if you have many time points and dynamic processes to visualize. Or do we talk about a slideshow when you have every 2 to 4 seconds a new frame, and this is suitable to show a few time points, but not to have a really nice, smooth visualization. Interactively, is it only a presentation somebody could watch, or is it something that you can also use for interactive analysis? So, and how here now I would like to show you an animation of this burger plane, which is one option you could use. And this was made by Blender. So I just included all our data sets and generated a mesh. And then I did this 3D morphing, but also with a blend of this colored ice field and the plane surrounding the stones, just colored in gray. Just check, start it again, because it's pretty fast. Yeah, you can see the movement right here and the shrinkage of ice. Just saying, only 5 years in between. Right. Well, this kind of animation is a pretty cool thing, because you can clearly identify some trends and processes. For a qualitative overview, this is pretty easy to convey, and you can efficiently use the space. The entire slide was covered by the spatial topic I like to communicate. and time is visualized by merging with the true time. Yeah. The problem is quantitative values, so for a deeper examination are pretty difficult to read. Comparisons between individual timestamps are even more difficult, and you have the risk of sensory overload. It is pretty cognitively challenging because a lot is happening in this short sequence. So when you ask me, what do I recommend? Static or dynamic visualization? I would suggest you use both. Yeah, it depends. Static methods are ideal if you like to communicate specific points in time and if you like to develop explorable visualizations, for example, for your colleagues, or to convince stakeholders which are deeper into the topic. But the dynamic methods are ideal to give a specific understanding of the process. Yeah, so to educate the public, to educate or inform stakeholders in the first meeting you will have, yeah, because they are pretty impressive. And when we talk about impressive or about impressiveness, just let me give you in the final minutes a quick outlook. What I do next. So a lot of things happened in the past. What we are doing right now with all this cool data we captured, is there something more we can investigate, we can use to make our visualizations even more immersive? And there are two questions that arise in my mind, some weeks, some months ago. And the first one is there a way to reduce the number of images that has to be captured and processed to save, on the one hand, time in the field to capture the data, but also storage space without sacrificing the photorealistic 3D visualizations? And of course, how can we make the collected data even more engaging beyond maps and visualization? And you can already see it here in the subtitle. I would like to focus on AI and virtual reality at this topic. In which way AI could help us here? I would like to introduce Gaussian splatting. Gaussian splatting uses the same input like structure for motion, still our pictures captured by the UAV, but we use a fundamentally different scene model. So right now we just visualized points, 3D points. The points have a color. The color is originating from the pictures. But when you zoom in, you have gaps between the points. And Gaussian splatting learns from the pictures how these gaps could be filled. Now, a point is not even longer represented by a point, but by a so-called Gaussian, which is a splat. So a more or less round splat, which has some feathering at the outside. This Gaussian has a specific position, a shape, color, and transparency. And all these Gaussians blend into each other. And by using these Gaussians and learning from the sea, you can generate really nice new perspectives, which don't have these gaps, like having the point cloud anymore between the points. This is a pretty fast way to generate a really nice visualization, and you don't need that much of pictures to get this full mesh-like presentation, which is really photorealistic. Why could this be interesting for 4D mountain and glacier monitoring? Same images, new experience. Yeah, as the data set is identical to that we use already in our UAV and also webcam campaigns. We don't need additional data. We can just use what we have stored on our devices. And it bridges a bit the gap between this analysis and experience part. So the point clouds are pretty nice to do all these measuring things. But now to get this nice visualization part, Gaussian splatting is a really interesting alternative to these point clouds, especially when you zoom in very much. And this brings me to the last point, communication and teaching. We only like to protect and save things we understand and see. Yeah, but this is usually the sentence I tell my students. So when you can experience glacier retreat firsthand, having a nice and impressive visualization, not just seeing a map 2D map like you have seen before, then maybe you can convince the stakeholders to get into dialogue, to outreach, and to do something. And to finish my talk, I will show you a first result of this fingerprint data set using Gaussian splatting and virtual reality, which is done by my master student, Lea Kubicek. And yeah, let's come to know her. So she is now working in virtual reality with the Meta Quest 3 Google, and she is moving along or on the glacier. Here you have some kind of information signs, and you can look into the surrounding here. You have the sound, yeah, you have wind noise, and yeah, this is pretty interesting. And now Lea just enhances the resolution of all these textures here, that you get even more the impression that you are right now on the glacier. And she also implemented a mode that you stand on the glacier tongue, and by pressing the button, the ice is melting. And then when the ice just is removed below your feet, you just fall down a bit, because then you have the feeling, okay, now there's only the stone. Ice is gone. And with these words, I like to finish my talk, and I thank you so much. The online, all people online and all people in the lecture room of Edgar to joining the talk. And of course, I'm open for questions. Thank you so much. Yeah, it just during the talk, I received a mail from our international office with a reworked cooperation agreement. So yeah, everything is in progress, and I thank you all so much for having the opportunity to talk to you. And if you have something in your mind you like to to join the forces, just let me know. Thank you. Have a great day. Hey, bye bye. Bye.